Hello, my name is Maximilian Grüner. Welcome to my talk on understanding video streaming algorithms in the world. Let's get started. First, I want to thank my collaborators Melissa Licciardello and Ankit Singla. I want to start out with a roadmap of what I'm going to talk about. We will first start with some motivation as to why we should care about video streaming and what this paper aims to contribute to the community. Next, I will explain how we set up our experiment. After that, I'll show results for some of the metrics we evaluated. I'll then talk about the limits of our work and what we still envision. Finally, I'll close with some takeaways from the experiments. So, why do we care? First, we can look at the global share of internet traffic by application. When we plot traffic for different applications, we see one thing. All of them pale in comparison to video streaming. Video streaming itself consists of a large variety of smaller players and a few really big ones, like Netflix, YouTube and Twitch. So there is substantial investment and interest from industry. Most likely, the larger providers are also using their measurements across their user base to optimize their streaming service. However, these optimizations are largely proprietary in nature and unknown to us. So being able to measure and observe the behavior of these optimized players has the potential to reveal interesting insights for academic work on video streaming. But how are things looking in academia? As a proxy, we can look at the number of Google Scholar citations over the years. We undoubtedly see a huge growth in interest over the years. This leaves us with the following situation. There are two sides of progress in video streaming: academia and industry. This talk will look at the following question: what do streaming algorithms in industry look like, and can we learn from them? First of all, we need to select representatives from both sides. On the academia side, we can use robust MPC as a stand-in. For industry, we want to pick a large, diverse set of services. We start out by including big global players, such as YouTube and Twitch. After that, we want to also select for smaller, regional, popular providers. Lastly, we obviously also want to select for providers which are prominent in their content niche, such as pornographic video websites. All in all, we obtained data for these 10 providers. Unfortunately, we had to leave out many commercial players like Netflix, Hulu and Amazon Prime, as their term of service agreements are very narrow and don't allow for automated measurements. Altogether, we conduct the following large cross-product of experiments. We test these multiple providers across multiple network traces sampled from different trace collections used in past work, across multiple videos on each provider, with each experiment lasting several minutes of streaming. In total, we measure nearly 10,000 minutes, roughly 7 days of video streaming. Next, I'll describe our measurement setup. First, we obviously account for the browser in which we play the video and for the server from which we obtain the video chunks to play. Next, we want to listen in on these connections to get more insight. Therefore, we put a local proxy in between. After this, we need to account for the fact that we want to simulate the player behavior under different network circumstances. This is done locally via a monitor class and a Linux tool, Traffic Control. Lastly, we aggregate the information from the different sources in a third class. This class reads the buffer state from the browser, the request response stats from the proxy, and the video metadata from the server. Here I'm showing what one such measurement looks like. We obviously have to see what throughput was emulated over playtime in accordance with some input network trace. This is measured in Mbps. The second thing we want to see are the player's decisions. These can be plotted as a rate played at a specific point in time. For example, at 300 seconds, we start playing a chunk whose rate was roughly 2.2 Mbps. At this time, the the bandwidth in the network trace is lower, roughly 1.5 Mbps. Before we can start looking at play behavior, we have to examine the fidelity of our measurement setup. We're using a proxy to handle log requests and responses. This means that it could potentially impact the player behavior. How can we be certain that the impact is negligible? In order to assess this, we run an experiment. We are given two streams, A and B. These we give to a user. We can ask this user, could you discern the stream by the quality of experience provided by either one of them? If the answer is yes, then both algorithms behave similarly. If no, it means they are different. We only did one modification to the setup. As a proxy for the human, we use the linear QE metric as presented in the MPC paper. This metric accounts for rate, rebuffering, and quality switches during playback. We evaluated this on static test traces and computed the mean for all providers with a 95% confidence interval. For most providers, we see only minor deviations in terms of the mean. For YouTube and ZDF, we see a larger deviation. However, this is within confidence intervals. With this, we conclude that the impact is negligible. We can now start looking at more interesting parts of the behavior of these streaming platforms. With the first metric, we want to look at the startup phase. Why is this interesting? Well, behavior at startup contains implicit assumptions over the user base. Maybe a provider assumes all the users use its service in their homes in Switzerland. This would indicate good connectivity in general, and therefore you could even start downloading the first chunk in a higher quality. In order to assess this, we chose to look at two measurements which can both be measured in times and seconds. 1. How long does it take for the stream to start up? And 2. How many seconds does it have preloaded in the buffer once it starts playing? This plot shows the mean with the 95% confidence interval as bars. We see that most streams start after having downloaded one chunk. We only have one outlier here, Twitch. This provider downloads two chunks instead of one. This might be due to this provider assuming that their users are well-connected home users. Next thing we notice is that the startup time roughly correlates with the time buffered in the beginning. Again, we have some outliers. In Arte and SRF, this doesn't hold. The explanation for this is because SRF, which is a Swiss public broadcasting station, downloads the first chunk at a much higher quality than Arte. So, we have handled the first important phase. What is the defining behavior directly after the startup phase? From this plot, we could assume there to be two phases. The startup phase, where we have a stable playback rate has to be found, and the stable converged phase, with fewer switches between video quality levels. Do providers always switch at the same frequency, or do they switch more often in the beginning and try to converge to a low rate of switching? In this graph, we'll look at the average switches between chunk downloads in terms of Mbps over percent played of the video. We use Mbps as to normalize the different bitrate ladders for the different providers. We only plot in the 60% in playback as we don't observe interesting changes after that. On a first glance, we see that we seem to have a switching heavy startup phase and a more stable converged phase. Each player though seems to converge to a different switching rate. Let us look at how academia differs from the industry for SRF. We notice that the larger switching frequency for MPC is prevalent. MPC switches a lot as it tries to follow the bandwidth very closely. SRF trades this off for a more stable playback. Matching the bandwidth very closely also means something else. You're not building a lot of buffer. This has an impact on the long-term risk management towards bandwidth drops of the player. Visually, one can again explain this risk management with the bandwidth graph shown earlier. We first add another axis to the setup which accounts for the buffer in seconds at a given timestamp. We now can plot the buffer over time graph. On this we can look at two specific instances. In the first, we see how the player manages to keep a given quality although the bandwidth drops. This is due to the fact that he has built buffer at an earlier instance. So how good is the risk management of the industry players? This graph shows the average buffer size in seconds over percentage played. We see that different players target different buffer sizes. This is especially clear when you're looking at YouTube and the MPC algorithm run on the YouTube data. One explanation for this difference could be redownloading. But what is redownloading? Imagine you have been playing at a relatively low bandwidth and you have filled your buffer with 4 chunks. Your playback is at the beginning of your buffer. Now the bandwidth picks up. This means you can do 2 things. Use this to download 2 chunks at a higher quality. This then would be normal behavior. Or you can replace the chunks already in the buffer with the higher quality chunks. This helps you up the quality faster in the scenario. This technique is called redownload. We now go back to the previous slide. YouTube could be downloading low quality chunks as a risk backup, which then are replaced at a later point by high quality chunks. When we don't do redownloads, just like an MPC, we're stuck with our risk averse decision. So you might have to play in a lower quality, although a better quality could have been available. In order to be able to play with a small buffer, one has to adapt to bandwidth changes quickly, as it is the case with MPC. Therefore, we have 2 parts to the buffer risk management: redownload and reactivity. We'll examine each of these, starting with redownloading. We can quantify redownloading in terms of bytes played over bytes downloaded. A value below 1.0 implies some redownloading. On the right side, we can see that many providers do not use the redownloading at all. On the other extreme, Arte plays less than 80% of the bytes it's downloading, using redownloading heavily. Note also that YouTube uses substantial redownloading, which aligns with its large buffer strategy that we saw earlier. Having quantified redownloading, we also need to look at a second factor connected to the buffer behavior: reactivity. So how does one measure this reactivity? To quantify reactivity, you can look at a part of the example graph where we have a bandwidth spike. After zooming in, we can discern 2 phases: pre-spike and post-spike. If we now plot the difference in rate of the pre-spike against the post-spike, we get a smooth picture of the rate change. We now test this on artificial traces, where we simulate a bandwidth spike at a specific timestamp before and after which bandwidth is stable. We look at the mean difference in rate post-spike with a 95% confidence interval shaded region. On the x-axis, we plot how many downloads in the post-spike range we account for. Although we didn't do a full evaluation of the mobile space, we started to do so for the mobile version of Vimeo. When streaming in a mobile setting, we might expect the player to react slower because there are typically more fluctuations in the throughput. We see that they roughly spike at the same point in time. The desktop version upgrades for a longer amount of time. This is probably due to the fact that the larger resolution beyond a certain point doesn't improve the perceptual quality on a small screen device. Second, we can again look at industry versus academia. As expected, MPC quickly changes with the bandwidth and the industry player takes its time. This is very pronounced in 2BTV as its bitrate data has very few steps, only 3, and the player adaptation logic is very conservative in terms of switching. These choices probably reflect their design assumption of a long-form video content with relatively stable home connectivity. But if we are so slow to respond to throughput changes, do we use all the bandwidth available or are we wasting it? This can relatively easily be measured. Just take the bandwidth available during the streaming process, which is the area under the shaded curve here. You then divide this by the inverse of the data you have downloaded. This gives us a ratio downloaded versus downloadable. The evaluation makes for a surprising picture. Even the best usages are at maximum 80% of the available bandwidth. YouTube is only using less than 60% of the bandwidth. We can speculate that YouTube isn't attempting to closely match stream bitrate to available bandwidth, rather settling for a good enough, stable quality. This might reflect that YouTube is an ad-driven service and they pay for every bit they deliver, and using less bandwidth could be a profit maximization strategy. We are now diving into the larger objectives of the play and their employed optimization. Along these lines, we examine another dimension of such optimization, the video quality metric valued by a service. Let us look at a theoretical video. This consists of 3 scenes. One static, followed by an action scene, again followed by a static scene. We might look at the behavior of a simple algorithm in terms of resolution and buffer occupancy. The simple player is aiming at keeping the same buffer level and best improve it. It keeps the same quality for the action scene and the static scene. On the other hand, we can look at a more complex player which is aware of the trade-off of certain scenes. It might start out with the same quality. In the action scene, it though knows that more Mbps means a larger increase in perceptual quality. This then is equaled out in the static scene, where we don't lose so much in terms of perceptual quality when playing at a low rate. This means that a more complex algorithm may prefer to download chunks of high visual perception values at higher bit rates, thus showing a larger deviation in such chunks compared to the average chunk. One measure of perceptual quality of a chunk is the WMF metric developed by Netflix. We attempt to quantify whether a player is showing such bias in favor of high WMF chunks. Are high WMF chunks downloaded at higher bit rates? The x-axis is the percentile of chunks by WMF. For example, 40 implies we are looking at the top 40% of chunks by WMF. The y-axis measures the difference of average WMF for these top X% chunks compared to all chunks. We compare Twitch with a simple bandwidth estimate based APR algorithm on the same video and traces. Twitch shows a much higher preference for higher WMF chunks, thus indicating that their player accounts for perceptual quality rather than only bitrate. With this, I would like to conclude the experimental part of this talk. We evaluated many things, but obviously we can't look at everything. Next, I will list some such items left to future work. One thing players could be optimizing on is the latency of the connection setup with the client. Better latency could indicate that the startup could be done at a higher quality. This extends naturally into the possible avenue of having different startup behavior in different regions. Do you, for example, get the initial same quality in South Korea when streaming from somewhere with poor connectivity like the US? Another subject we only touched on is the mobile versus desktop comparison. Lastly, it might prove fruitful to deepen the investigation into the optimization objective employed by the larger providers. So, what have we learned? Stable streaming is important to industry players. Long-term stability of streaming algorithms, such as through setting an explicit buffer goal, could be part of future algorithm development. Relatedly, buffer goals differ and probably also depend on the fact of whether redownloads are available or not. Another important finding is that the bandwidth across the players is not used fully. This indicates that optimization objectives could potentially be different from those in academic work. For example, operating at a different point in the bandwidth cost versus client experience trade-off. Finally, there are also areas where recent academic work is seemingly in alignment with industry. The goal of optimizing for perceptual quality like WMF has recently appeared in academic work and seems to be in play for at least some providers. With this, I'd like to conclude my talk, and I'm now open to questions. Thank you very much.